welcome back again to the channel. On this video we're going to discuss problem 2 from chapter 1, Baby Rudin's principle of analysis. So the question is to prove that there is no rational number whose square is 12. Before we get started, as usual, please give it a try. So please pause the video for a moment. Alright, let's get started. Suppose on the contrary, we could find such rational number a over b such that its square is equal to 12. So let's call the rational number to be a over b. So then the square of a over b, which is a squared over b squared, is equal to 12. And this 12 can be written as 2 squared times 3. Now dividing both sides by 2 squared, then we obtain this equality, that a squared divided by 2b squared is equal to 3. So this tells us that if there is a rational number whose square is equal to 12, then there is a rational number whose square is equal to 3. And let's recall that rational number to be p over q. Right, so this p over q here. And then we can assume more about this p over q. For every rational number, we can always write it in the simplest form, which means that the common factor, the greatest common factor, is equal to 1. So here we assume that the greatest common divisor of p and q is equal to 1, which means that there is no positive common factor greater than 1, right? So then this p over q, because by the existence of a rational number whose square is equal to 3, then this p squared over q squared is equal to 3 over here, right? Then, okay, we just in this line. Then if we multiply both sides by q squared, we obtain p squared is equal to 3q squared. And in particular, we can see that the 3 is a factor of p squared. And this is an abbreviation of how to write down 3 is a divisor of p squared, or 3 divides p squared. So in particular, we have that 3 divides p squared. And then we claim that if we have a number, we have a square such that those square is divisible by 3. So the claim is like this: if 3 divides p squared, we claim that 3 must be dividing p as well, right? So what can be wrong if 3 is not dividing p? If 3 is not dividing p, it means that when we divide p by 3, we get a remainder. And the remainder can be either 1 or 2. In other words, p can be written as 3s plus 1, or p can be written as 3s plus 2 for a certain s in z, for a certain integer s, right? Okay, so we are in this situation that p is written as 3s plus 1, or p can be written as 3s plus 2. Now what's going to happen if we square this number? So let's take the first situation when p is equal to 3s plus 1. So when we square that p, we get, what is the square of 3s plus 1? 9s squared plus xs plus 1, which can be factored, which can be written in this form. So this is 9, and 9s squared is 3 times 2s is 6s, and that's plus 1, right? Okay. So what this expression tells us? This expression tells us that p squared is a multiple of 3 plus 1, which means that p squared is not a multiple of 3. And that contradicts the fact that 3 divides p squared. And similarly, when p is equal to 3s plus 2, when we square that 9s plus 2, we get 9s squared plus 12s plus 4, which can be written in this form. That's 9s squared, and that's 12s, and that's 3 plus 1, which is 4, right? And again, we can see that this p squared is not the multiple of 3, because it is a multiple of 3 plus 1. So therefore, if 3 is not dividing p, then p squared is not a multiple of 3. Therefore, we must conclude that 3 divides p, which means that our claim is correct, right? So now let's get back to our equation that p squared is equal to 3 squared. And from the claim, we know that 3 divides p, right? So then we can write p as 3 times something. P is equal to 3 times t, okay? Now plugging back this p equals to 3t to that equation. So we get this, and therefore we have 9t squared is equal to 3q squared, right? And then upon dividing both sides by 3, we have 3t squared is equal to q squared. But now we are in similar situation as in this equation. So we can see here that 3 divides q squared. So according to lemma, if 3 divides a square of something, then 3 divides those numbers. So since 3 divides q squared, then 3 divides q. But now we are in trouble. What is the problem with that? So here we have that 3 divides q, and also we have 3 divides p. Therefore, 3 is a common multiple of p and q. Meanwhile, at the beginning, we already declared that p and q has no common divisor, has no greater divisor but 1. But here, we can find another divisor greater than 1, a divisor of p and a divisor of q as well. So there's a contradiction. Okay. Since we arrive at a contradiction, therefore, the very beginning presupposition that there is a rational number whose square is 12 must be false. Therefore, there is no such rational number. Okay. So the conclusion is that it's not possible to have a rational number whose square is equal to 12. Okay, so that's all for today. Thank you very much for watching. See you again on the next video. Bye-bye.